Find the minimum pipe diameter, capital D, in inches. In this problem, a concrete sewer pipe positioned at 0.5% slope conveys the sewage generated by a population of 30,000 people. The maximum allowable D over D is 0.70, and the peaking factor and generation rate are provided. Since the depth of water in the pipe is at most 70% of the pipe diameter, then the diameter of the pipe is at least the depth of water in the pipe divided by 0.70. Our strategy will be to utilize Manning's equation, solve for the area and hydraulic radius, and then develop an expression for the left-hand side of this equation in terms of the diameter D and solve for D directly. Let's begin by solving for the right-hand side of this equation, which equals the flow rate times the roughness coefficient divided by K times the square root of the slope. We have been given the slope, which is 0.005, or 0.5%. The problem states the pipe is concrete, so we can look up its roughness coefficient, N, in a standard table of values. The roughness for concrete is most always 0.013. When Manning's equation is used with English units, the value of K equals 1.486, or 1.49. Lastly, we turn to our flow rate, Q. The average flow rate of sewage through the pipe equals the total population, P, times the average sewage generation rate. For sake of space, we'll abbreviate this generation rate R sub AVE. However, in sewer design, we want to account for the peak flow rate through the pipe, which equals the average flow rate times a peaking factor, PF. This peaking factor is a function of the population. Plugging in our known values for the population, the generation rate, and the peaking factor, after its value is calculated using a population of P, the peak flow rate computes to 4.96 cubic feet per second. 4.96 is then plugged into the variable Q, in addition to the other three variables, and the right-hand side of the equation becomes 0.6137. The units have been dropped from this equation at this step, so we'll have to keep in mind that the area is in units of feet squared and the hydraulic radius in units of feet. Now it's time to develop an expression for the left-hand side of the equation in terms of the pipe diameter, capital D. We can divide and conquer this problem by solving for the area and hydraulic radius separately. If we increase the pipe figure and define the angle theta, from geometry we know the cross-sectional area of the water equals 1/8 times the quantity theta minus sine theta times the diameter squared. And the hydraulic radius equals 1/4 of the quantity 1 minus sine theta divided by theta times the diameter. In both of these equations, theta is measured in radians. To find theta, we'll take a closer look at this triangle, or more specifically, half the triangle. Since we're solving for D over D equal to 0.70, we'll substitute in 0.70 times the diameter for the depth. Since the radius is half the diameter, we know the small leg of the triangle is 0.2 times the diameter, and the hypotenuse of the triangle is 0.5 times the diameter. Knowing this is a right triangle, the angle defined as alpha equals the arc cosine of 0.2 times D divided by 0.5 times D, which equals 1.159 radians. From the diagram, we observe theta equals 2 pi radians minus 2 times alpha, or theta equals 3.964 radians. This value of theta is next plugged into the equations for area and hydraulic radius. And the area equals 0.5873 times the diameter squared. And the hydraulic radius equals 0.2962 times the diameter. Returning to the previous equation, these values for the area and hydraulic radius are substituted in for A and R. And after a few lines of algebra, we find the minimum allowable diameter, D, is 1.137 feet, which equals 16.54 inches. This diameter must be rounded up to the nearest possible solution, which equals 18 inches. Answer C.